In the rest of the section, we're mostly talking about symmetry and about stretches and compressions. So we're looking at this particular graph, and this one, it happens to be symmetric about the origin. And the reason why it's that is because if you could rotate this all the way around from the origin, it would duplicate itself down here, versus say something about like this where it's just reflected about the y-axis, or something like this where it's reflected about the x-axis. So in this particular example, the graph is reflected about the origin. It's symmetric about the origin. And then here are your stretches and compressions. So when we've got something multiplied by this scalar or this coefficient, it's going to stretch it up. So something, here's the 1 time, and then here's 2 times. It's definitely going to stretch it up. And then if we did half, then that's going to shrink it or compress it. And in this example, it's telling us that we're doing a compression. We're doing a stretch by 2, I believe. It says scientist is comparing a fruit fly population to another population whose growth follows the same pattern, but it's twice as large. So what we want to do is we want to translate our values. We want to stretch our values by a factor of 2. So our 1 here becomes a 2. Up here we've got about a 3, so that's going to become about a 6. And then down here we've got about a 2, so that's going to become about a 4. And then our 7 is going to stay the same. So this one is going to look something like that. And here's our revision right there. And then let's see the next one. This one is asking us to, this is a transformation of f of x equals x cubed, and it wants to relate the function g of x to f of x. So what's happening here? It looks like it's being compressed, but let's see what it normally should be. So think about values that make sense in this example. So if we did x equals 1, then f of x should be 1, which we don't have. What do we have? Looks like it's about 0.25. So right away, I'm already thinking that the scalar is going to be 0.25, but let's do a couple more just to make sure. So if we had x equals 2, that would give us f of x equals 8. So 2 should be 8, so this would be 6, 7, 8 should be here, and instead it's at 2. So yes, it looks like we're doing a factor of 0.25. So our g of x equals a quarter f of x. Or if you wanted to keep the decimal, you could do 0.25 f of x. And this one is just showing a combination of stretches and compressions. So our original function is usually written in the blue, and that's your toolkit function of x squared, your typical quadratic function. And then what happens when you multiply it by a 2 is it's going to become really steep. Steeper and steeper the bigger that number is. And then if you multiply it by a fractional part, it's going to stretch it out. It's going to take even longer to get to those higher values. And then this is just another real world example of making compression. It's talking about the same fruit fly population. The new population progresses 1 hour the same amount as the original population did in 2 hours. So you can see it's shrinking, it's compressing it horizontally.